Now, first things first, we have the integral B, which is tonight. So just to remind you guys, it is in 7 o'clock in Stores 110. You may want to show up just a few minutes before 7 o'clock, like maybe quarter till or 10 till or something like that. Go ahead and get your seat, get yourself signed in, and we'll go ahead. I think it starts promptly at 7 o'clock, and then typically how the integral B works is you have different rounds. The first round, they're going to give you a nice piece of paper with 10 integral questions on there. And like I said, these are not overly difficult integrals. I mean, yes, it's going to be basic rules, use substitution, integration by parts, partial fractions. That is the worst thing you'll see. It's things that we teach you guys in here. I'm not going to make you memorize Formula 103 off of your tables and expect you to know that one to be able to integrate this problem. It doesn't work like that. But we may, towards the end, to make them a little more challenging, do a combination of integration by parts with a U substitution or something like that to see how you guys do on those things. But it's about, one, getting it correct, and then later on in the process of the integral B, when we narrow down the list to the top 10, 20 candidates or whatever, then we start doing kind of a time issue. We give you a question, and then not only do you have to get it correct, you've got to get it correct before everybody else gets it correct. So we start putting the time aspect on there. But the first couple of rounds is going to be basically 10 questions where we actually just go through and give you, 10 minutes, 1 minute per question type thing here. You turn that in, they grade it, and then they take the top winners off of that one to get it to round 2, to round 3, and round 4 before they start narrowing down the list and stuff like that. And so a lot of people ask me about how am I going to distribute the partial credit points that this thing is going to be worth. Well, it depends on how well you guys do. And again, it depends on how many rounds they end up having. But let's say you made it through the first 2 or 3 rounds or something like that before you were eliminated. Well, you'll get 5 points added onto your next test. If you get past round 2 or 3 or 4 or something like that, then I may add another extra 5 points on there, and you get 10 points on your next test. Most I'm going to add is 15 points. And if you make it to the final round and you get some of this prize money or whatever, we'll split it, and I'll give you some extra points on that. So the most I'm going to give is up to 15 points on this one, but it basically depends on how well you progress it, because I want my students to do well. I think last year my student won. That's always good. The year before that, it was my wife's students won, and I never heard end of it. So I want my guys to win. So go compete and win for me. Make me look good. All right, so there you go. But it's tonight at 7 o'clock in Stores 110, which is across from the architectural building. So let you go right across the little quad right in here in front of Fretwell. All right. Last time we were discussing work with springs. So we had 2 formulas you need to know. Work, well, first off, on springs, work for force is equal to Kx. This is called Hooke's law. And we know that work is equal to the integral of force dx, and that's always the case. So when you apply this, we get a special formula for springs, which is that work is equal to the integral from A to B of Kx dx. So this is a formula you need to know, and you need to know Hooke's law, force equals Kx. The big other thing you need to know about this particular material is very simply this. When you start measuring springs, you measure the distance of springs from their natural length. It does not require any work at all for the spring to be sitting there at quote-unquote rest. If the spring's just sitting there, that's where we start measuring it from. And then we start pulling it or pushing it or whatever to get the oscillation in there. And by pulling it, how much force it takes to do that, or by pushing it, how much force it takes to do that. So you have to start measuring from the natural length. Now, last time we did this particular problem, and I called it a type 1 problem. Type 1, I gave you force, and then I asked you about work. This is the traditional problem, because when you do a spring problem, the most important thing to be able to get the problem started out correctly is you got to find K. Every spring is defined by its spring constant. And we just don't just throw in your face, okay, one time on a final exam 5 years ago, they gave the students K. But other than that, throughout the years, we don't give K. We make you go find K. And we give you, so the first thing you got to do to any spring problem is find K. So when they tell you a force of 40 newtons is required to hold a spring that's been stretched from its natural position of 10 centimeters to 15 centimeters, that information right there is just used for one thing, to find K. And then once you find the K off of that, then you figured out how much work is done going from 15 centimeters to 18 centimeters. The other aspect of this stuff is you got to pay attention to units. We're talking about with the metric system, we want work to be measured in joules, Newton meters, or in the English system, we want the work to be measured in foot pounds. So if they're talking about inches, you got to convert inches to feet, and they're going to be a fraction of feet divided by 12. So you got to pay attention to units to make sure you're in either feet or you're in meters, and depending on the circumstance. So, and we did this problem last time. So let's take a look at this one. This is a type 2 problem because there's only really 2 types of problem that we give you with this stuff. Again, my 2 formulas, force equals kx, and work is equal to the integral from a to b of kx dx. So here we go. It says this. This is one of the work given, work and force is asked about. 7 joules of work is required to stretch a spring from its natural length of 20 centimeters to 50 centimeters. How much work can be done in stretching spring from 25 centimeters to 35 centimeters? How far beyond the natural length will a force of 25 newtons hold the spring? All right, so remember the first piece of the puzzle is used to figure out what K is. And what did they give me? They gave me this. 7 joules of work is required to hold a spring from its natural position of 20 centimeters to 50 centimeters. So here's 20 centimeters, labeling it. This is my natural length, my natural position. This is where the spring was sitting literally at rest. And we took this and stretched it all the way over here to, looking at my numbers, this is relative, this is where the 50 centimeter mark is. And it took 7 joules to be able to stretch it from here all the way out here. But what does joules measure? Because here's the trick right here. Work. This is not, they didn't give me force, they gave me work. Now, let's pay attention to your units. Natural length has got to be zeroed out. You got to calibrate your system. So when they start talking about 20 centimeters being the natural length, this is going to be your 0 mark. So this is 0 centimeters, which means your 50 centimeters is actually stretched out how far? 30 centimeters. You take your distance, and always, I don't care what distance you have, you always subtract your natural length. That's your pattern. So you subtract 20 from 50 and you get 30 centimeters. But you also notice the units. It's centimeters. That's bad. What's the standard unit of length in the metric system is meters. So to convert it to a meter, you divide by centa, you divide by 100. So 0 centimeters is the same thing as 0 meters. However, 30 centimeters is 0.3 meters. I take 30 and divide by 100 because there's 100 centimeters to a meter. Does that make sense? Now, this is the information right here. I'm going to figure out what K is. But they gave me work. We have a formula for work. Work equals the integral of kx dx. Work was 7. This is the integral from 0 meters to 0.3 meters of kx dx. These are your bounds, 0 to 0.3. And you look at this thing and go, hey, this is an integral, but there's still an unknown in this guy. You can still use this integral form to be able to solve for k. Let me show you. So 7 is equal to, now integral of kx dx. Now integrate with respect to x, k is a constant. It holds over. Integral of x is x squared over 2, evaluated from 0 to 0.3. According to the fundamental theorems, you plug in top minus plug in bottom. So 7 is equal to k times 0.3 squared divided by 2 minus k times 0 squared divided by 2. Well, 0 squared divided by 2 is 0, so that part goes away. And putting this in my old calculator, just to show you what I'm getting here. All right, so I've got 0.3 squared divided by 2 is 0.045. So 7 is equal to 0.045 k. And now I can solve for k. The first part of any spring problem is used to figure out what K is. So this cancels, and that leaves me K is equal to 7 divided by 0.045 is 155.55556. I'm just going to make it convenient for myself and convert it to a fraction. That is 1400 over 9. That is my K value. Now, let's go and answer the questions. There's a Part A question here. Part A asks you this. How much work is done in stretching a spring from 25 centimeters to 35 centimeters? So if this was 20 centimeters, here is your 25 centimeter mark. Here is your 35 centimeter mark. And the question is, how much work is done in stretching a spring from 25 centimeters to 35 centimeters? Again, the first thing you got to do is you got to calibrate your system. Zero out that natural length. It's a zero system. So if the natural length was 20, that makes 25 centimeters equivalent to 5 centimeters. And it makes 35 centimeters equivalent to 15 centimeters. Subtract off your natural length. Subtracting off 20 centimeters because you really are talking about stretching it from 5 centimeters from its natural position to 15 centimeters from its natural position. It doesn't require any work for the spring to be at equilibrium. Does that make sense? But it's still in centimeters, so I've got to convert this to meters. So 5 centimeters is 0.05, 5 centimeters is 0.05 meters, and 15 centimeters is 0.15 meters. I divided 15 by 100 and 5 by 100. Does that make sense? So for Part A, to calculate the work, it'll be the integral from 0.05 to 0.15 of kx dx. But k was equal to 1400 over 9x dx, because there's my k value. Does that make sense? Now, let's integrate. Work is equal to 1400 over 9 is a constant. Integral of x is x squared divided by 2, evaluated from 0.05 to 0.15. I'm going to clean this up. 2 goes into 1400, 700 times. 700 divided by 9 times x squared, evaluated from 0.05 to 0.15. And then according to the fundamental theorem, plug in top minus plug in bottom, I get 700 over 9 times 0.15 squared minus 700 over 9 times 0.05 squared. And that's clearly calculator time now. So it's 700 divided by 9, let's put parentheses around my fractions here, times 0.15 squared minus 700 divided by 9 times 0.05 squared. And I end up getting the answer, work is equal to 1.5555556. What would my units be? This is the metric system. Work is measured in joules. Newton meter is also acceptable, but joules. Does that make sense? But for this problem, there was a Part B. Part B question was this. How far beyond its natural length will a force of 25 newtons hold the spring? Pay attention to units. 25 newtons. Newton measures what? Force. So they're giving me force is equal to 25 newtons. And they're asking me how far beyond the natural length. You know what variable measures how far beyond the natural length? That variable is x. Basically, they're asking for x. In the famous formula, force is equal to kx. X represents the distance beyond the natural length you stretch the spring. K represents the spring constant. F represents force. They gave me force. They gave me 25 newtons is equal to K. K, by the way, if you wanted to do it, was 1400 over 9, same spring. And if you wanted the units on K, it being a metric system, it's newtons force per distance per meter, Newton per meter. So K is equal to 1400 over 9 times x, where x represents the distance from the natural length, which is basically what you want to solve for. So to solve for this guy, I would divide both sides by 1,400 over 9. And I get x to be equal to, put it on the handy dandy calculator, 25 divided by 1,400 divided by 9 gives me 0.1607, it's web work, so enjoy, 142857 watt. Good. This is where you're talking about the metric system, so the standard unit length is meters. So honestly, if you wanted me to sit there and really tell somebody exactly how long a force of 25 newtons would stretch a spring, 0.16 meters is about 16 centimeters. Does that make sense? But the units would be meters with the decimal. Does that make sense? Did I lose you guys anywhere? Remember, in any kind of spring problem, they're very straightforward and basic, but the first piece of any information about a spring problem is used to figure out K. And once you get that K, you just integrate K dx, Kx dx, and start basically doing the formula, because remember, work is equal to the integral of force dx, and with springs, we have a very special force formula called Hooke's law, force equals Kx. All right. Moving on. This next section is on basically fluid and pumping liquids out of tanks. Basically, we call it work done by pumping. Okay? Now, typically, what we have here is we either have the metric system or we have the English standard system. And typically, we're talking about liquid. And the standard liquid we're going to use is going to be water. Okay? So what we know about water is up here. Water has a density of 1,000 kilograms per meter cubed. But when we're talking about work, remember, work is equal to force times distance also, work is equal to the integral of force dx. And we also have this, which is the formula that I will be using. Work is equal to the sum of the change in force times the distance. In the old formula, I said the distance you have to lift, but now it's going to be the distance that you're going to have to pump. This is going to be my formula that we'll be using it. But it's all pretty much set up for the same concept here. The problem is density tells you pretty much mass per volume. That's what density is, kilograms per meter cubed. But to turn mass into weight or force, you got to multiply it by gravity. So what I call water weight, that's equal to your water density times gravity. Now, what is the water density? Water density is 1,000 kilograms per meter cubed. What is gravity? What is gravity? And this is the metric system because it's a meter cubed. So what's gravity in the metric system? Things we're supposed to know, 9.8 meters per second squared. So when you multiply these two guys together, you're going to end up getting 1,000 times 9.8 is 9,800, and you're going to end up getting a kilogram times meter per second squared per meter cubed. Now, I wrote it like this just to put all my units together, but a kilogram times meter per second squared is also known as a watt. Kilogram measures mass, meters per second squared is gravity or acceleration, and F equals ma, so this is actually force in the metric system. And what is force in the metric system measured in? Newtons. So this is 9,800 newtons per meter cubed. So when I'm talking about water with the metric system, you take your density of water and multiply it times gravity. But the density of water is constant. It's 1,000 times gravity, 9.8. It's 9,800. It's a number worth memorizing. However, on certain problems we're going to do in here, they're going to change it from water to something else. Famous problem you have on well work will be a hot chocolate problem. And where in the hot chocolate problem, the density of hot chocolate is different from water. So they're going to give you what the density of the hot chocolate is, but you've got to remember to multiply it times gravity to get the force out of it so we can find out this change in force. Also, we may do some problems with, since gas prices are going back up again, we may pump some gas out of tanks and stuff like that. Well, any kind of liquid. Gasoline will have a different density, and therefore you multiply it times 9.8 gravity, and to be able to get the actual force out of it. This is all done within the metric system. The metric system problems, they're going to give you density. You got to multiply by gravity to get the quote-unquote force or weight out of it. However, when it comes to the English system, we just pretty much give you what we call water weight. What does water weigh? Well, we round it off, but we're going to say it's 62.5 pounds per foot cubed. And it's just a constant you're going to memorize. And if we give you any other kind of liquid, we're going to tell you what that weighs per foot cubed, per volume. Force per volume. Does that make sense? Now, if you guys ever lifted any water, you know water actually weighs a lot. You know, all these folks from 100 years ago that had to go down to the creek to get the water for their house and stuff like that, and had to bring it up in buckets. You got to feel for these people because they had to go bucket after bucket after bucket, or be better, let's get a bigger bucket. Yeah. Water weighs 62.5 pounds per foot cubed. Foot cubed, foot by a foot of water actually weighs 62.5 pounds. It ain't light. If you ever played with water, you know. Okay? So, but it's hard to describe in terms of what does this water weigh in terms of the metric system. It's 9,800 newtons per meter cubed. So if I have a meter by a meter by a meter of water, it's going to weigh 9,800 newtons. But for most of us, you know, metric system is kind of still a little bit on the, we're not sure about the numbers and stuff like that, what it means, because we all grew up with the pound system here. We know that a foot cubed of water weighs a lot, 62.5 pounds. But these are constants you need to know. Now, here's a problem right here, so I'm going to kind of set this one up. This is about the easiest kind of problem I can give you. So let's set this thing up. We have here a cylindrical tank. And this is a big cylindrical tank, and we got this upright where the radius of the cylindrical tank is 5 meters, and it has a height of 20 meters, and we're going to do something special. We're going to stick this thing 5 feet below the ground. So we got this big tank that is a 5 meter radius, 5 foot radius. 5 foot radius, it is 20 feet long, and it is sticking under the ground, 5 feet under the ground. So we buried this thing. This thing is all full of some kind of interesting liquid. Let's say it's water for this example. And we want to pump all the water out of this tank. Does that make sense? There's my setup. So, to be able to do this problem, I'm going to come over here and do the next page, and I've got enough work, the page here, that I can actually write this thing up for you. So this is the work for this particular problem. So let's draw this thing up. First thing you want to do is draw your tank. Our tank is a cylindrical tank, sitting upright. It has a radius of 5 feet. It has a height of 20 feet. We have up here ground level, and we were told that the tank is 5 feet, the top of the tank is 5 feet below the ground. That was all the given information I just gave you. Okay? And it's full of water. Full of water. We want to pump all the water out of the tank. Anytime you do any kind of work problem, whether it be lifting rope and a baby attached to it to the top of the well, or some kind of a bucket and you want to lift it to the top of a building, you still got to set up your coordinate axis. Because you got to make all these numbers relevant and relative to each other. Traditionally for me, I like to put the coordinate axis at the bottom of a tank. Listen up. I will always put it at the bottom of a tank just to make my numbers positive. It's easier for me to explain it to other folks. You can put your coordinate axis anywhere you want to. As long as you integrate over your right numbers, you'll still get the same answer I do. There's no problem there. But since I have to explain it to others, I like to put the coordinate axis at the bottom. It makes all my numbers positive. The only time I do not put my coordinate axis at the bottom of the tank is when the tank has a cross section of a circle. To make the numbers easier for me in terms of the equations, I will put it in the center of a circle. I like to put my equations at the center of a circle when I have a cross section of a circle, but when it's just a cross section means the side of the tank is circular. This one, the side of a tank is actually a rectangular shape. So I'm going to put my coordinate axis right down the middle, because of symmetry, right down the middle. Here's my coordinate axis. Here's my x-axis. Here's my y-axis. Now I'm going to put my numbers. Here is 0 at the bottom. The radius is 5, so this will be 5. This will be -5 on the other side. It has a height of 20, so this mark right up here is 20, which means the ground level, here is ground. What level would ground be at relative to my coordinate axis? 25, 5 feet above the top of the tank. So now all my numbers line up. There's 0 at the bottom, top of the tank's at 20, ground level is at 25, and my target is to get the water to the top of the tank. Does that make sense? So here we go. Here's my formula. Work is equal to the sum of the delta force times the distance that you have to pump. It is the same formula that I used to pull baby Jessica out of the well, except for instead of the pumping, where we're lifting the baby out of the well, now we're pumping the water out of the well. Delta force, however, is going to be something new for this particular problem. It is going to be your water weight, or whatever liquid you happen to be dealing with weight, in this case it's water weight, times the delta volume slice. We're still doing this quote unquote the slice method. So what I'm going to do over here to do this problem is I'm going to come up here inside my tank where the water is, and I'm going to make a little horizontal slice, a little delta Y slice. Remember, work is all about lift. And the natural axis to integrate with respect to when you're lifting is the y-axis. When you read Dr. Stewart's book in chapter 7.6, he is a big fan of doing dx. And he likes to do similar triangles with this stuff and to try to integrate with respect to x, because everybody likes to integrate with respect to x. Well, yeah, x is great. We integrate most things with respect to x. However, when it comes to work, I'm going to rewrite the book a little bit here for you guys. Work is about lift. And the natural axis to set up an integral with is not going to be a dx axis. It'll be a dy axis. You want to do dy. It's easier to set the thing up with. So I'm going to show you guys how to do this stuff. Okay? So now, I'm going to come over here and make a little delta y, and I'm going to slice it. So if I slice this guy, use my little Ginsu knife, and you got to visualize this. If I slice this as a cylindrical tank, I'm going to take a little section out of this cylindrical tank. Now pull it over here, and it's going to be, in this case, it's going to be a little disc. When you slice a tank horizontally, there's only two shapes you're going to get. It's either going to be box shape or it's going to be cylindrical shape. This one's cylindrical shape because we're talking about a cylinder, and we're cutting it along the y-axis. When this thing's standing up, this thing is going to be a little disc. It's either going to be disc or a box. And you got to know the volume. The volume of a disc, because it's a cylinder, I'll call this delta volume because it's a little change here, is going to be pi r squared h. It's a cylinder, pi r squared h. If it was box shape, it would be length times width times height. But it's circular, so it's pi r squared h. Now, what you need to know in this problem is, what's the radius? Well, this thing is vertically shaped, so this thing, it doesn't matter if I make the slice down here or made the slice up here. The radius is the same throughout the tank. And what is that radius? It's a constant. What is it? The radius is 5. What is the height of this here little section of tank? because we made a little delta Y slice, it is actually delta Y tall. We're not talking about the whole thing. We're talking about that little individual slice that we took out of this tank. It is delta Y tall. So that's why I call it the delta volume. So your delta volume is going to be pi times your radius, which is 5 squared, times your height, delta Y. So I clean that up. That's going to be 25 pi delta Y. Does that make sense? So now that I've got the formula for the little delta Y change, so understand what's going on here. I made a slice somewhere in the middle of the tank. I could have made it at the bottom. I could have made it at the top. And the reality is I'm making all these little slices. But they're all going to look kind of the same. So it's like little poker chips. Here's a poker chip for the middle. Poker chip for the top looks the same. The bottom all the way down. That's why we're going to sum them up. When you sum up all your little stacks of these little delta volumes, you get the volume for the whole thing. Does that make sense? Now, delta force is equal to water weight times your delta volume slice. What does water weigh in this problem? Very important. Pay attention to units. This is how you pass a physics class. This is also how you're going to pass the calculus class in terms of these kind of problems. There's two constants for water. It's either 9,800 newtons per meter cubed or 62.5 pounds per foot cubed. Which one we're going to use? 62.5 pounds per foot cubed, because all my units were measured in feet. So I know this is an English problem. So water weighs 62.5 pounds per foot cubed. The little delta volume slice is 25 pi delta Y, and this is a little volume here. So it's officially in feet cubed, just to let you know that your units end up canceling. That's why it's a change in force. So your delta force ends up being equal to 62.5 times 25 pi delta Y. And I'm just going to clean that up on my calculator. 62.5 times 25 is 1,562. So my delta force is equal to 1,562.5 pi delta Y. You with me? Now, watch what I do. Work is equal to the sum of that delta force times the distance that you have to pump. Catch a pattern. I'm doing the same thing as what I did with that baby Jessica problem. Watch. Work is equal to the sum. My delta force, we just calculated to be 1,562.5 pi times delta Y times the distance that I have to pump. The slice that we made was somewhere between 0 and 20 inside the tank. It was at an arbitrary Y level. What is my target? Where are we trying to pump this water to? We're trying to pump the water 5 feet above the top of the tank. This is why your coordinate axis is so important. 5 feet above the top of the tank made a target of what? Where's my target to hit the water to? 25. 5 feet above the top of the tank. So what is the distance that I'm going to have to pump this water? It's a distance. Distance is either calculated top minus bottom or right minus left. This is we're doing verticals. This is top minus bottom. What is it going to be? 25 minus y. 25 minus my arbitrary y level cut. The target minus arbitrary y. You'll see that a lot. Now, here comes the beautiful world of understanding integral calculus. Convert this problem over. So work will be equal to, now 1562.5 pi is a constant, goes out front. Summation turns into integration. You've got 25 minus y is your function, and the delta y turns into a dy in the back. And all I got to do now is put the bounds. And I mentioned this to you guys last time. You integrate over the part that you want to remove, where the stuff is you're removing. We are removing all of the water out of the tank. All of the water out of the tank. Where is the water at? Not where it's going. We got where it's going with that 25 minus y. This is important because this is where most people will screw this up. They'll put the wrong bounds on this thing. Where is the water at relative to the tank, relevant to my coordinate axis? Where's the water at? From 0 to 20, it was full of water. That would be my bounds. The 25, where we're going, is up here. That's taking part of that distance pump stuff. We've already got the 25 taken care of. You just integrate where the water is that you're going to remove. Does that make sense? So now, work is equal to 1,562.5 pi. Integral of 25 with respect to y is 25y minus integral of y is y squared over 2, evaluated from 0 to 20. According to the fundamental theorem, you plug in top minus bottom, plug in bottom. So this is 1562.5 pi times 25 times 20 minus 20 squared over 2 minus 1562.5 pi times, when I plug in 0, pretty much I get 0 and that part goes away. And I end up getting work is equal to, and I'm going to stick this on the old calculator, 1562.5 times parentheses 25 times 20 minus 20 squared divided by 2. And I just want to show you guys, and I'll blow this up for you guys in the back there, to show you, let you know that exactly how I'm typing it in. The only thing is, it had pi in the answer. I left pi off. I'll leave pi in the actual answer I write up. 1562.5 times 25 times 20 minus 20 squared divided by 2. I end up getting what? I get 468,750. Stick the pi back on there, and you got to put me units. No units, no credit. What is the answer to this problem? We found work in the English system. What is it? Foot-pounds. Does that make sense? It looks like a large amount of work, but if you do enough of these kind of problems, you're going to catch a pattern very quickly. Now, this is the nicest thing I can give you because this was vertically on the side. But I got a question for you. Before I move on to my next tank, my question is this. I want you to set up the integral for pumping half the water out of the tank. And here's the beauty of it. The setup is exactly the same. We're talking about the tank is 5 feet below the ground level. This is a cylindrical tank. Height is 20 feet. Radius is 5 feet. Everything is exactly the same on this thing. So my integral is going to be exactly the same. And that integral is this. Work would be equal to 1562.5 pi times integral of 25 minus y dy. The only difference is your bounds. Now, the question is, what are my bounds going to be? It's from 0 to 20 is where the water is. Well, we want to do half the water. Half the water would be a mark of 10 in the middle, right? Halfway between 0 and 20 is 10. So the question is, do I integrate from 0 to 10 or do I integrate from 10 to 20? That's the question. What's going to be my bounds? I hear 10 to 20. I hear 0 to 10. That's my question. Because if you get it right, you get the right problem right. If you put the wrong bounds on there, it's a 15-point problem. We'll take 20 points off because you obviously weren't paying attention. So, which one is it? I hear 0 to 10. I hear people confused. All right. So, all right. Have you guys ever pumped water or any other liquid out of a tank? Oh, sure you have. Let me give you an example. You ever seen anything that looks like this? Thank you. It's a cup. Okay. It's a cup. Have you ever drank water out of a cup? All right. It's full of water, right? There it is, full of water. Now, we can't lift this cup because this cup is awfully heavy. It's got some liquor in it or something. It's very heavy water right here. Whatever we got in this thing, very heavy. So if you've got a big container that's heavy and you need to drink the stuff out of it, what do you use? A straw. You need some kind of pumping device. A straw. Have you ever pumped liquid out of a tank? Yes, you have. Because everybody's used a straw. Go to McDonald's, Hardee's, or Burger King, or any of these guys, and they give you a straw in the bag. Here it is, and we know what to do with it. We stick it through the little hole in the top of the cup, and we put it in there, and we drink it. We are pumping the liquid out of the tank. So the question is, when you pump the liquid out of the cup, do you pump the bottom part of the liquid or the top part of the liquid? Because you integrate over the part that gets removed. My question to you is, what gets removed? The top of the liquid or the bottom of the liquid? So when you're pumping this thing, what gets removed? You guys are stuck, because I hear people saying the top of the liquid, bottom of the liquid gets removed. Well, yes, you suck it in from the bottom, but have you ever noticed that when you stick a straw into the liquid, the straw fills up to the same level that the liquid is within the cup? So when you actually drink the stuff out of the cup, are you drinking it from the top or the bottom? Since the straw fills up to the same level as the liquid, whether it be Dr. Pepper or whatever, in the cup. It's the same level. So it's the same idea. When you tip the cup up, you're drinking the top stuff or the bottom stuff. What gets removed is my question. The stuff at the top. So let me just show you a picture. After I drink the cup, where is the other half of the liquid located at? Is it just floating up here at the top because you removed the bottom liquid and all of a sudden this stuff just floats at the top? Or does gravity kind of like pull everything down and your liquid is down there at the bottom? You integrate over the part that gets removed. So when you're drinking stuff out of a cup and you drink half the cup, the stuff that's left over is still in the bottom. The top part got removed. Does that make sense? So, based upon that, when you pump half the liquid out of the tank, the bottom part liquid will still stay there. It's the top part that got removed. You integrate over what's removed. The answer to the question is you would integrate from 10 to 20. Pay attention to your bounds. You integrate over what gets removed. Does that make sense? Liquid just doesn't float out there in space because we're not in space. Gravity tends to pull it down. So when you drink half the liquid, the top part gets removed, the bottom part will still remain in the cup. Does that make sense? You integrate over what gets removed. That's a very important concept as we set this stuff up. But again, this problem, it was one of our easier problems. Why? Because when we made our slice, it didn't matter because this was a vertical side. Vertical problems where the tank is vertical on the side is the nicest one. So if you turn the page, let's see if we can make it a little more interesting for you guys. Here's the tank right here. It says this. An inverted cone in the shape, an inverted cone shaped tank has dimensions. The height is 12 meters. The radius is 4 meters. The tank is completely full of water. Find the work done pumping all the water out of the tank to a level of 3 meters above the top of the tank. So again, the top of the tank, we got this little straw thing in here where we're going to be sucking all the water out of this tank. So here's how you do it. First thing you got to do is you need to redraw the tank and put a coordinate axis on it. With this one, here's my tank. With our coordinate axis, once again, I'm going to put it at the bottom, right here at the tip. This is 0. So how tall was this tank? This tank had a height of 12 meters. So this is 12 at the top. It had a radius of 4 meters. So here's my little circular part. So the radius over here is 4. This officially would be -4 because of symmetry. Okay, this is my y-axis. And we're supposed to pump it out 3 meters above the top of the tank. So 3 meters above the top of the tank, according to my coordinate axis, is at 12. Where would 3 meters above that be? 15 meters. This is my target. Keep that in mind. This is where I'm trying to get the water to, is 3 meters above the top of the tank, the mark of 15. Does that make sense? So, work is equal to the sum of the delta force times the distance you have to pump. Delta force is equal to water weight times your delta volume slice. So once again, I'm going to come over on this tank, and I'm going to cut somewhere on this y-axis, and I'm going to take that little section and lift it to, my goal is to get it up here at 15. But when you got to visualize this, when you take a little vertical slice out of a cone-shaped tank, what's it going to look like? When I make my little slice, I slice it this way. It's either going to be disc shape or box shape. What's this one going to be? It's still going to be a disc because you're taking this little section out of it, right? So it's going to pull it over here. So it looks like this. And it is delta y tall. And it's disc shape. So my delta volume formula is going to be pi r squared h. This will be delta volume is going to be pi times r squared times delta y. The question is, here's the important question, pay attention, what's the radius? We got a problem. The radius at the top is 4, but I didn't make the cut at the top, did I? I made it somewhere down here. The radius at the bottom is a point. The radius would be 0. So I can tell you right now, the radius is somewhere between 0 and 4. But it varied. Whether I made it up here, it would be a little bit larger. Made it down here, it would be a little bit smaller. So it varies, which means you need a variable. Anytime when you're plotting points and you move away from the y-axis, what direction are you going into? The x. You plot points. You go over x, up y, right? And so I'm moving away from the y-axis, so my radius would actually be equal to x on this guy. This would be an x radius. So your delta volume is going to be pi x squared delta y. So to calculate my delta force, what is the water weight in this problem? Pay attention to units. What is my water weight in this problem? What is it measured in? All the distances are measured in meters, which means I need the water weight of, density of water is 1,000 kilograms per meter cubed times 9.8 meters per second squared, which makes it what? The 9,800 number. It's either going to be 9,800 or 62.5, or we're going to give you some kind of weird density, and you're going to have to multiply it by gravity because you got hot chocolate or something or other. See what works. So your water weight, because it's a metric problem, is 9,800. Your delta volume slice is pi x squared delta y. So work, which is equal to the sum of the delta force times the distance that you've got to pump, work is going to be equal to the sum of your delta force, which is 9,800 pi x squared delta y. Just plugged it in there. What is the distance that I'm going to have to pump? Catch a pattern. I made a slice somewhere in the middle of my tank, and it's an arbitrary y level. My goal is to take this level of liquid and pump it. Where am I trying to get it? 3 meters above the top of the tank, relevant to my coordinate axis. Where's that at? 15. So what is this distance right here? Top minus bottom. What is it? 15 minus y. There's a pattern with this stuff. Now, converting this summation into integral calculus. Work is equal to summation turns into integral. The 9,800 pi is a constant, so I like to stick those guys out front. X squared times 15 minus y, and the dy always shows up in the back, delta y always shows in the back as dy. And I got a problem. What's my problem in this one? The problem is my tank is on a slant. And because your tank is on a slant, you've got an x variable in the middle of my integrating with respect to y. I got to get rid of that x variable. And how you do that is very simply this. You got to figure out the equation for edge of tank. Now, look at it from a two-dimensional perspective. The edge of the tank is right here. It's a line. It's a line that goes through the origin, 0, 0, and it's this point over here on the top of the tank is the radius was 4, the height was 12. So you're going through the points 0, 0, and 4, 12. It is a line. So you've got to come up with the equation of that line. Classic point slope formula. I need the slope. The slope is change in y over the change in x. So that'll be 12 minus 0 divided by 4 minus 0. So my slope is equal to 12 over 4, which equals 3. Now I need the equation of a line, so I'm gonna use the point slope formula. Y minus y1 equals m times x minus x1. I'm gonna pick a point. I'm going through these 2 points, 0, 0, and 4, 12. What's the easiest point to use? Yeah, 0, 0, clearly. So I'm gonna use the point 0, 0, and I got my slope. So this will be y minus 0 equals my slope of 3 times x minus 0. So you get the equation y equals 3x. That is the equation for the edge of the tank. But the purpose of this equation for the edge of the tank that you had to come up with is to get rid of the x variable and convert him in terms of y. So as y equals 3x, that means x is equal to y divided by 3. And I go and plug him right in here. So work is going to be equal to 9,800 pi times the integral of y divided by 3 squared times 15 minus y dy. And the only thing now I've got to do is put my bounds on this thing. Where's the water at? This thing was full of water, and they want to pump all the water out of the tank. Where's my variable? What's my bounds? 0 to 12. Because that's where the water is. Don't try to integrate up here to 15. There's no water up here. That's what you're trying to do, is get the water up there. The water's in the tank. So here is, and you can see in terms of how we're going to ask questions like this on the final exam as well as problems on my test and homework sets. Set up the integral that calculates the work. And then on something like this, just to save some time, I will use my calculator and leave the answer in terms of pi. So this is 9,800 math integral from 0 to 12 of parentheses x divided by 3 squared times 15 minus x, close parentheses, dx. And these are big tanks, so they're going to be a big amount of water, big amount of work here. So I end up getting work is equal to 3,763,200 pi watt. Very good. This was a metric problem. Newtons with the meters, Newton meter, aka a joule. There is the amount of work done. Does that make sense? So from this point on, all we're going to be doing is doing pumping problems and all different kinds of shapes of tanks that we can come across, with this hemispherical, the other box shape, and the famous tank on the side. So we'll do those next time. See you guys then.